on the solutions to systems of linear equation. Now I'm going to begin with a new topic altogether, that is solutions to ordinary differential equations, okay? Specifically boundary problems, okay? That's IBPs, okay?
Numerical methods for solving ordinary differential equations. Now, we've already seen solutions to differential equations in Math 105, that's Engineering Mathematics 2, okay? And just to introduce ourselves to numerical solution, we want to recall our analog methods of solving, let's say, a first order differential equation. Like we have to find a solution to the differential equation y prime is equals to 3x, given that y at x0 is equals to 2. Okay, good. So we're saying that the solution to this system should be a function y which satisfies the differential equation y prime. Okay, and to solve this analytically, we can find a solution, okay, using a number of techniques, okay, depending on the form in which the equation can be put. So we can use the exact methods, we can use the separable methods, integrating factor approach, etc. Okay, good. So looking at this equation, we can easily separate it into the function what y of x and g of x. So as what dy is equals to 3x dx. Okay, that we find the integral of both sides. That will be the integral of dy is equals to the integral of 3x dx, which will give us y on the left side is equals to 3 over 2x squared plus c, the constant of integration. So that gives us the general equation, okay, or the general solution, okay. But given the initial conditions at x equals to 0, y was equals to 2, we can find c by substituting the value of y and x into the general equation to get what c is equals to 2. Hence the specific what solution to the system as what y is equals to 3 over 2 x squared plus what plus 2. Okay, so this gives us the specific solution or the specific function which satisfies the first order differential equation specified at the given initial value. Okay, so we refer to this as the analog system of finding the solution to differential.
Yeah, so before we proceed, try and get your calculators with you. Okay, then we continue with the presentation. Make sure you have your calculators with you, and then we continue with the presentation. Okay.
Now, the first point we have to know is that we are limited when it comes to the use of analytic solution or analog techniques. Okay, in what terms? In terms of its speed. It gets more tedious for some questions. You may have to spend close to like 5-10 minutes solving given differential equation. Okay, but real life problems are more complicated differential equations, and you need the solutions quick to make decisions. hence we cannot rely on analog techniques. Then again, some systems, what I mean is some differential equations cannot be solved using analytic method, any of the analytic methods we have looked at in class. Okay, hence for an approximation technique, and numerical methods help us to address that challenge. Okay, so we say that method based on algorithm that will enable us to use a computer to arrive at what? Approximate solutions to differential equations.
Okay. So among many techniques which we'll be making use of today or in the next coming weeks is the Euler's method. We'll also be looking at the Taylor series, okay, method. We'll also be looking at the run-shooter, okay, approximation techniques, okay, and then we'll see how to also write algorithms or programs, okay, which will implement this numerical procedures, okay, for finding the solution to the differential problem. Now, we're told that given the first order differential equation, okay, y of x, okay, that's y prime of x, which is f of xy, okay. In other words, your first derivative, f of xy, as we work, f of xy, okay, is your function y prime. Take note of that, okay. So f of xy is what? The first derivative, okay, the first derivative, okay, which has been provided in the question. Good. And then you also give it initial conditions. Y naught will be written as what? Y at x naught, okay. And then we'll be asked to find what? The value yi, or the solution yi, okay, at various points, okay, at various points, which we'll demonstrate graphically in the next word, in the next slide, for I is equals to 1, 2, 3, 4, and so on and so forth. The Euler's method of approximation, okay, is this equation we have here, is this function we have here, that is y at a step 1, I plus 1 is equals to yi plus h times f of x I y I, okay. And then take note, the f here is the derivative function that was given originally, okay. So let's explain this whole process of iterative solution to the system. So what we are saying here is we got a point, okay. You are given an initial point, x naught, y naught, okay. And then based on x naught, y naught, you're going to find the value of y1, okay, using an approximation that is, let me go to the next slide. Okay, so from s naught, y naught, you're going to use an equal step size, okay, and then find an x1, which is x naught, s1 is x naught, okay, x naught plus the step size, okay, plus the step size, okay, Then based on this value, we find y1, which is what? Y naught, okay? Y1 is y naught plus what? The step size times the derivative function at what? X naught, y naught, okay? So in other words, this is the increment from y naught, okay? So we keep looking at the small increment, the small change in y, okay, as x changes with a common what? Step size, okay? So we're going to take it. So from x1 to s2 is another what? Plus h. So which means that x will keep changing at what? X naught plus what? I times what? H, where I is 1, 2, etc. Okay, so when I is 1, that's the first iteration. When I is equals to 1, we have x naught plus h. When I is 2, we have s naught plus 2h. When I is 3, we have x naught plus what? 3h, and so forth and so forth. And then you keep looking for the corresponding y1, y2, y3, y4, okay, values. That will help us to get an approximate curve. Okay, so if this is y2, okay, then eventually we are getting an approximate curve of the function, which is demonstrated in the next slide, okay, as shown. So this is it. Okay, so that help us to get what? The solution of the function, okay? So, and we know that the solution of a differential equation is the function, is the function whose derivative satisfies what? The differential what? Equation, okay? So, whilst we are finding the increment in x with the corresponding increment of y, we are getting a curve, okay? A curve based on what? These various points, which will approximate the curve of the actual solution to the derivative what? Equation. So this is the whole idea behind what? These numerical solutions to differential or IVPs, okay, first order differential equations. Okay, now let's move on. So we have an example here, okay, which says that we are supposed to find, let me bring this here a bit. Yeah, we have to find what? We are to, given that y, the first derivative, y bar is equals to t minus y over 2, okay? Use Euler's to find the solution to the system, given that y at x naught is equals to 1, and then the step size h is what? 0.1, okay? Over the interval t from 0 to 1, okay? So now let's attempt that. Like we said that the function for the Euler's approximation is what? Initially we wrote it at yi plus 1, okay, is equals to yi plus what? H times f at x naught, or x at, yeah, I, okay, I, and then y at what? I. Very good. Yeah, so instead of I, this time we have it in terms of what? N, okay? So your N is going to be what? 0, 1, 2, 3, 4, etc. So we are saying that per this formula we see here, then if N is equals to 0, then this will be Y 0 plus 1, so that would be Y1. And then this side will be what? Y0, Y subscript 0, plus the step size H, and then function x okay, is so in the formula that would have been x0 and then y0, okay. But let's take note that the differential equation is not a function of x, okay. It's not a function of x, right? It's rather a function of what? T, okay. So your independent variable in the function x in this formula changes to what? To t. That is why we have in the formula t naught, y naught, okay. Very good. And then we've been told that y naught, okay, y naught, like we said, y naught is the value, the initial value condition, okay. Y naught is y at s equals to 0 has been given as 1. So y naught is 1. Step size is what? 0 has also been provided as what? 0.1. So this gives us what? 0.1. And then your function, okay, is the derivative function given. Okay, the derivative function. We said that the function f at xn, okay, yn is equals to what? The first derivative function, that's y prime. Okay, good. So which means that this f at t naught y naught is this function t minus y over 2. Okay, but t naught, so t naught, let me write it this way. So this is the same as t naught minus what? Y naught over what? Over 2. Okay, t naught minus y naught over 2. Okay, now t naught is what? T naught is initial value will be what? 0. So initial value is y at t naught. T naught was 0. Okay, so we have 0, okay, minus y naught was what? 1. Y naught was 1. That's the initial conditions over what? 2. Okay. And then when you do that calculation, this is minus 1 over 2 times 0.1 will be what? Minus what? 0.05. Okay, and 1 minus 0.05 should give us 0.95. Okay, is it clear to everyone? Is the solution clear to everyone? Is the solution clear enough to everyone? Hello, class. Okay. Very well. So let's continue. Edna, is the solution clear?
Yes, sir.
Very well. Okay. So once you've obtained your first, okay, approximation, you move to the next step where n is equals to 1. If n equals to 1, then the formula now becomes what? y1 plus 1. So that will be y2. Okay, is equals to y1 plus h times f at t1, y1. Okay, very good. Now y1, as we know, is 0.95. Your step size is always 0.1. Okay, it doesn't change. But your t1, like I said, the t keeps increasing from this point, okay, So just like we saw on the x-axis, okay, this time the axis is t, and we are starting from 0 to 1, okay, but with a step size of what? 0.1. So it keeps increasing by 0.1. Then it will go to 0.2, okay, 0.3, 0.4, 0.5. So you keep going till you get to what? 1. Okay. This is the incremental step. So we have T1 is 0.1. So that you substitute into the function. And Y1, 2, you've already calculated it to be what? 0.95. So you substitute it here, okay, over 2, okay. So when you do this calculation, you get negative 0.85 divided by 2, okay, times that should give us 0.425, okay, times 0.1 should give us 0.0425, okay, plus 0.95 should give us what? 0.9075. Okay, so this is the second approximation. Okay, then you move on to the third. N equals to 3. So n equals to 3 means that we've moved from t of 0.1 to what? T of 0.2. Okay, so this n equals to 1, n equals to 2, n equals to 3. So your t keeps moving. Okay, so you substitute those values once again. Okay, and then follow the same process till we get this value, which is 0.87215. Okay, which means that whilst you're working, you're going to generate a table with the corresponding steps. So at n equals to 0, that's initial point, you have t 0, y is 1. At n equals to 1, t was 0.1, okay, y was 0.95. At n equals to 2, t was 0.02, y is what? 0.85. You have to find at n equals to 3. This will be 0.13, and then you need to find this, okay? So you're going to continue till you come to, okay, 0, till you come to what? 1.0, okay? You keep going at the same intervals, meaning you go, step 4 will be 0.4, okay, step 5 will be 0.5, step 6 will be 0.67. Yeah, so that's the reason why I said you should get a calculators, okay? So at this point, you're going to do the next 3 iterations for me, okay, and then get back to me with your solution. So get the next 3 iterations, the next 3 approximations for me, okay, and get back to me with your solution. I'm waiting for you.